Hello? Okay, it's okay. Okay, this is a joint work with Alex Andoni, Zhong, Cliff Stan, and Zhong Yuan. Recently, several parallel systems, such as MapReduce, Hadoop, and Spark, have become very successful in practice. And this success has sparked renewed interest in new algorithmic ideas for these parallel systems. So one of a very important theoretic direction is to develop good models for these parallel systems and to relate them to classical models such as PRAM model. One of the models is called massively parallel computation model, or just the MPC model. And I think this is a very good model in the sense it balances the accurate modeling with theoretic elegance. So today I will talk about how to design a graph connectivity algorithm in this model. Okay. So before I talk about our algorithm, firstly, let me introduce the model. So you have input data, which has size capital N. And in your system, you have P machines, each with some local memory size, S. And before the computation, the input data is arbitrarily partitioned into these machines. And so each machine just holds a part of the input data with size at most order of S. And in our work, we care about the most restrictive case. So in this case, the number of machines times the local memory size is just linear in the input size. This means that in your system, the total space available is just linear in your input size. And furthermore, the local memory size is sublinear in the input size. This means that there's no machine can hold the entire data. So to compute the final results, they should to communicate and coordinate to each other. And just for simplicity, you can just assume in the system you have square root n number of machines, and each machine just holds square root n the local memory size. Okay. And the computation in this model proceeds in rounds. So at the beginning, so each machine just holds a part of the input data in its local memory. And then in each round, each machine can do some local computation based on the data stored in its local memory. And then at the end of this round, each machine can send messages to arbitrary other machines. However, there's a restriction. So in a single round, each machine can send or receive the data with size at most S. This is because each machine just holds the local memory with size at most S. So it cannot send or receive more than S data because it cannot hold that data. And the data received by a machine in this round will be stored in its local memory, and it will be used for the next round computation. Okay, so for example, so in a single round, one machine can send, so for example, if you have square root n machines and each machine has square root n local memory size, in a single round, one machine can send square root n other machines, each with a unit size message. Or it can send just one machine message with the size square root n. Okay. So at the end of the computation, the output is distributed on some output machines. So they output so they just store the output distributedly. And our goal is to design algorithm which minimize the number of rounds for the computation and the communication.
So the machines are labeled?
Yeah. So they're indexed. So yeah. So yeah.
The computation in each machine is unbounded. The computation
right. So in this model, the computation is unbounded, but for our algorithm, actually for each machine, we just need a linear in the input of this machine computation. Okay.
round, right?
Yeah, each round. Yeah. Nearly linear. Yeah. Okay. So I think the MPC model is a very natural approach to describe parallel distributed computation. So it just repeats the following 3 steps. Okay, so question.
What's the difference between this and Valiant's bulk synchronous parallel model?
Oh, so for the BSP model, so actually they're very similar. But for the BSP model, you also care about the local computation. But here for the MPC model, we think the bottleneck is the synchronization. So we only care the number of runs. Okay. Yeah, so actually there is a variant of the BSP model, but we care about different complexity. Okay, so for the MPC model, it just repeats the following 3 steps. So it divides the input data into several small parts. And each machine just handles a single part and then compute some partial solution. And then the machines just combine these partial solutions and output some data for the next round computation. So let's compare it with the classic PRAM model. So the MPC model can capture the power of local computation. This is because in the MPC model, each machine has very large local memory. So you have the power to do some local computation. And actually, there are some fast algorithms for some specific problems. For example, for the XOR, you have an n-bit string, and you want to compute the XOR of these n bits. So in the PRAM model, you need log n number of runs. And the best algorithm is log n number of runs, and the lower bound is also log n. But in the MPC model, you can do it in constant number of runs. Another example is sorting. So for sorting in the PRAM model, the best algorithm is also log n number of runs, but there's a lower bound is also log n. But for the MPC model, sorting can be done in constant number of runs. And actually, all the PRAM algorithms can be simulated in the MPC model with the same number of runs. So if you have a PRAM algorithm, then you have the MPC algorithm with the same number of runs. But it is possible to design a better algorithm in the MPC model. So why should we study graph problems in MPC model? So the graphs, especially for these large graphs, I think they are very natural benchmarks of this parallel distributed computation model. So in our real life, there are many large graphs. For example, for the social networks, transportation networks, or internet, they have million or billion number of vertices and edges. So we need some large-scale computational system to handle this kind of the data set. And furthermore, the dependencies between the vertices and the edges of this kind of large graphs may be very complicated. So we often need some non-trivial and novel algorithmic ideas to handle this kind of issues. And actually, there's a long line of works which study the graph problems in MPC model. For example, for the graph connectivity, maximal matching, minimum spanning tree, vertex edge covers, or min cuts. And the graph connectivity problem is a very fundamental problem. So this is why we should study this problem in MPC model. Okay. So what is graph connectivity problem in MPC model? So what's your input? So suppose you have an n-vertex, m-edges graph, undirected graph. The input is just all the edges of this graph. And you can just use m pairs to describe this graph. So your input size is m. And this is also your total memory. And at the beginning of the computation, the edges is distributed on the machines arbitrarily. And we want to output the connected components of this graph G. So one question is how to represent connected components of the graph. Actually, we can use n pairs. Each pair is a vertex color pair. It means that we assign each vertex a color. And actually, these n pairs in the end of the computation can be distributed arbitrarily on the output machines. And for any two vertices V and V prime, they are in the same connected components if and only if they are assigned by the same color. So here is an example. So your input is this graph. It has 7 vertices and 9 edges. And it has 2 connected components. One is a for-click, contains the vertices 1, 2, 3, and 4. Another is a triangle, which contains vertices 5, 6, and 7. And in our system, we have 3 machines. At the beginning of the computation, each machine just holds 3 input edges. So for example, for the first machine, it contains the edges 5 to 6, 1 to 3, and 1 to 4. And for the second machine, it contains 2 to 3, 3 to 4, and 6 to 7. And for the third machine, it contains 1 to 2, 5 to 7, and 2 to 4. Then after several rounds of the computation and the communication, at the end, there are 2 machines which output some pairs. So for the first machine, it output 4 pairs. It means that it assigns the vertices 1, 2, 3, and it assigns vertices 1, 2, 3 the color 3 and assigns the vertex 5 the color 6. And for the second machine, it assigns the vertices 6 and 7 the color 6 and assign the vertex 4 the color 3. So if we look at these 7 pairs together, we know that the vertices 1, 2, 3, and 4 are in the same connected component. And vertices 5, 6, and 7 are in another connected component. Okay. So there are several previous work study this problem. So just remember, so in all the cases, the total space is just the number of edges. So the total space available is just linear in the input data. And we just use this small n to denote the number of vertices. Then in the scenario when your local memory size is much larger than the number of vertices, let's say n to the 1 plus some small constant, then this algorithm can do it in constant number of runs, and it's called some filtering technique. And later on, people found that even when the local memory size is linear in the number of vertices, we can still do it in constant number of runs. And actually, we can simulate a congested click algorithm in MPC model when your local memory size is linear in your number of vertices.
So when you say the space is n, you mean?
Oh, so this is a local memory, yeah. So for
big O of m, or is it just m?
Which one?
The first one. The total space is m, and what's the unit?
Oh, so when it's a dense graph, for example, m is n to the 1.5,
Yeah.
then this local space is sublinear in your number of edges. So in this scenario, we can do a constant number of runs, but the total space available.
That's not my question. So the local space is the space that each memory.
Each machine, yeah, right.
What's the meaning of total space? Is
Oh,
it the sum of all the local?
Yeah, some of the all the local space.
But then is big O, or is you insist it should be equal to m? Is it big O of m or m?
Big O of m.
Oh, it's big O. Okay.
Yeah, it's linear. Yeah, it's linear in the.
Yeah,
Yeah,
it doesn't say.
sorry. So yeah, so it's linear in the number of edges. So you can you can
You
have
have
a
extra.
you have extra space.
Yeah.
So actually it means that if you have more edges, you have more extra space, and we will use this property in our algorithm. So for a dense graph, you have a better algorithm. This is because just a trick. Because if you have more edges, then you have more extra space. Yeah.
Thank you.
Okay. Yeah. Okay. So, but the problem becomes very hard when your local memory size is much smaller than the number of vertices. And the best algorithm known previously is just the log n runs algorithm. And actually, there's a log n runs algorithm in PRAM model has been known for more than 35 years. And because, as I mentioned before, we can simulate any PRAM algorithm in MPC model with the same number of runs. So it directly gives a log n number of runs MPC algorithm. And there's another simple randomized log n runs algorithm in MPC model. However, all the algorithms known previously needs log n number of runs. We don't get any better algorithm before. Okay, so here is the main question. So can we design an MPC algorithm for graph connectivity which is faster than log n number of runs? And the local memory size is more than the number of vertices. Because as I mentioned before, if your local memory size is linear in the number of vertices, then you can do it in constant number of runs. So the only interesting case is when the local memory size is much smaller than the number of vertices. So there's a log n lower bound for tuple-based MPC model. So the tuple-based MPC model is a variant of the MPC model. It has more restrictions of the messages you can send and receive in each round. And the log n lower bound is also conjectured to be necessary in the worst case in MPC model. However, if you can prove a super constant lower bound, then it will imply a very strong circuit lower bound. So it seems to be hard to prove a super constant lower bound in MPC model. There are some recent developments of this problem. So for the random graphs, one can show that we can do it in log n number of runs to find all the connected components of these random graphs. Question?
You say random graphs, you mean are the vertices like randomly indexed?
So random graphs means that each edge appears with some probability independently. Yeah.
Is that just, that's for any probability of edge sampling?
I think the hard case is when your graph is very sparse. So I think each edge is sampled with probability log n over n like that. Yeah. And later on for the, there's another algorithm which takes log n number of runs and can find all the connected components with a good spectrum gap. So in other words, it can find all the well-connected components. Here we state our main result. So we give a faster, fully scalable algorithm for the connectivity problem. And we bypass the conjectured log n lower bound by parameterizing the round complexity as the function of the diameter of the graph. So the diameter of the graph is just the largest diameter of all of the connected components of this graph. And precisely, our algorithm takes log diameter times log n number of runs, where the base of the second log is m over n. So it means that if you have more edges, then you have more total space. So you can do it better. So when the graph is very dense, let's say n to the 1 plus some small constant, then this number of runs is just log diameter runs. And actually, parameterizing in diameter is very standard in distributed computing literature. And there's another heuristic algorithm in MPC model, which is conjectured to obtain log diameter number of runs. However, in our work, we also show a counterexample for their algorithm. And furthermore, our algorithm is fully scalable. It means that our algorithm can work for any local memory size. Any means that for any constant, and your local memory size should be m to some small constant. And our algorithm works for general graphs, so we don't need to make any assumption of the input graph. And for the special cases I mentioned before, for example, for the random graphs or for the graphs with a good spectrum gap, because for this kind of graphs, the diameter is at most log n, So our algorithm only takes log n square number of runs. So it's just slightly worse than the algorithms I mentioned before. But our algorithm works for general graphs. Okay, so now let's go to the technical parts. Before I talk about our algorithm, let me first introduce a general algorithmic framework. And it's called the leader contraction framework. So, okay, it's a question.
Is this what's known about this problem where it's degree 2 graphs? Is it trivial?
Oh, for degree 2 graph?
Yeah.
For example, so if you, okay, so as I mentioned before, there's a conjecture. So for this omega log n conjecture, what's the conjecture? So it's very, so conjecture is very hard to distinguish the following two cases. So in the, so your graph has 2 cycles or have 1 cycle. If you want to distinguish these 2 cases, the conjecture, this needs log n number of runs.
So degree 2 is
right. So when you are, so I believe that if your diameter is very large, then you need log n number of runs. But I don't know how to show this. And maybe it's possible to prove some conditional lower bound, but I don't know. Yeah.
But this is the hardest case.
Yeah, right. For the 1 cycle and 2 cycle, this problem is very hard. Conjecture to be very hard. People don't know how to solve this. Okay. Okay, so what is the leader contraction algorithm framework? So how do you find the connected components? Actually, each time we can choose some leaders, and then we try to contract the non-leader vertices to the leader vertices. And then we can repeat to do this until each connected component contract to a single vertex. Okay, so formally, we have an input graph G, undirected graph, with the vertex set V and the edge set E. We initialize the iteration counter I and let the first graph G1 to be the input graph. And firstly, we check if there's no edge in the graph. So each single vertex is a connected component. Then we can just output. Otherwise, we randomly choose some vertices from the current vertex set as the leaders. And I will talk about how to choose the leaders later. But now you just assume you have some leader vertices. And then for each non-leader vertex, if there's a leader U, which is the neighbor of this non-leader vertex, then we try to do the contraction. We want to contract the vertex V to the vertex U. So what does contraction mean? So contraction, so if we want to contract the vertex V to vertex U, we just check all the edges. If there's an edge, okay, so if an edge has a one endpoint, which is vertex V, then we just replace this endpoint to vertex U. And then after we do this operation, we just remove all the duplicated edges. And we also remove the self loop. And if there are multiple choices of the leader neighbor U, then we can just choose some arbitrary one. Then we let Gi plus 1 to be the contracted graph. And then we repeat this leader selection and then the contraction, this procedure. And finally, when each connected component is contracted to a single vertex, then we can output. So for example, if vertex V is finally contracted to the vertex U, then we can assign V the color U. Here's some example. So we have input graph this tree, and the beginning G1 is this tree. And then we randomly sample some leaders, these red vertices. And for each non-leader vertex, if it has a neighbor leader, then we try to contract this non-leader vertex to its neighbor leader. For example, for this non-leader vertex, it tries to contract to this leader vertex. And for this non-leader vertex, it has two neighbors which are leader, then it can choose an arbitrary one. So it chooses this leader neighbor. And for this non-leader vertex, it chooses neighbor leader, this one. And for this non-leader vertex, because it has no leader neighbor, so we do nothing for this non-leader vertex, and we also do nothing for this non-leader vertex. And then after we do the contraction, we have the falling graph. So this one contract to this one, and so this vertex is this vertex, and this leader vertex becomes this vertex, and these two non-leader vertex are contracted. Okay. And then in the next round.
Oh yeah. So when you do contractions, how do you store? Like, do you store and remember that like A contracted to B, and does that build like a tree structure?
Yeah, right. You can do that. So yeah. So in our algorithm, okay. So in this framework, so how do you know what's my kinetic component? So when you do the contraction, you just record this pointer. So at the end, then you have several tree structure, and if I want to find whether U and V are connected, then we can just find the root of the tree.
The leaders don't change from round to round?
Sorry?
The leaders don't change from round to round, or do you change?
I change it every round.
You change.
Yeah. So in this round, I have this kind of leaders, right?
Yeah.
Then, okay. So now I have this graph. And this graph has the leaders in this one and have the non-leader vertices, which has no leader neighbor. And then I randomly choose the new leaders in the contracted graph. Then I do the contraction.
Right? Oh, these are random picks?
Yeah, I just random pick the vertex.
That's how you pick leaders?
Right, but okay, so random pick, you have many choices how to pick the leaders. For example, you can choose each leader with probably 1/2, but if you always choose each leader with probably 1/2, then you always need log n number rounds. So I will, so in our algorithm, we give a smarter method for choices of the leaders. So this will give our faster algorithm. I will talk about it later. Okay. Yeah, so you just now you just assume you have Oracle, then I can choose some leaders, and then I try to do the contraction. It's just the leader contraction framework. Yeah. Okay, so question.
When you have the tree at the end, you need to like compact it down to like a one height tree, right? To actually
Right. So you can do it when you do the contraction procedure. You can also do it in the end of the algorithm, because the number of iterations you need for the contraction is the height of that final tree. So you can just simply do the contraction for that tree at the end, or you can also do it in every single round. Yeah.
So in this model, there is a space bound again. So like, why is contraction not increase crossing my space bound?
Okay. So actually, so this will relate to some of the implementation detail in the MPC model. So how do you do the contraction? Actually, you can, okay, so firstly, how do you represent the leaders? So for the leaders, you can use the n pairs. Each pair is a vertex Boolean value pair. And it means that, okay, so for this vertex, if the Boolean value is true, then it's a leader. Otherwise, it's a non-leader vertices. Okay, then, so for each edge, I want to know whether one endpoint is a non-leader vertex or leader vertex, and another endpoint is a leader vertex or non-leader vertex. So how to do this? You can just do the sorting and build a B-tree structure and to do the query and to know whether that endpoint is a leader or non-leader. So if for this edge, if one is a non-leader vertex and another is a leader vertex, then because for each non-leader vertex, it will have many leader neighbor. It may have many leader neighbor. You can use sorting again, then to contract a non-leader vertex to a leader vertex. So you know for each non-leader vertex, what's my parent? So what's my neighbor leader I should contract? Once you know this, then you can also do the sorting again. Then you do the replacement. So because sorting can be done in the linear total space and with constant number rounds. So you can do this in MPC model. Yeah, but it's really the details of how to implement this in MPC model. Okay, so you randomly choose leaders again, then you do the contraction, you have this graph, and then I randomly choose leaders, and then I do the contraction again, then I have this one. Finally, we have a single vertex. Okay, so yeah, as I mentioned, so how to represent the leaders in the MPC model, you can just use the vertex boolean value pair. And then because I mentioned before, you can use this sorting, these primitives, so the contraction, this operation can be done in constant number of runs once you have the leaders.
It's worth noting that this idea goes back at least to John Rife in 1982, who did the
Oh, really? Okay.
unbiased coin flipping and got a login PRAM randomized algorithm on a concurrent read, concurrent write model.
I see. Okay.
Yeah, there's a lot of prehistory.
Yeah, I think this is very common in the parallel literature because it's a very general idea. If you want to find the connected components, you just find some vertices as leaders and do the contraction and continue to do this. And finally, you find every connected component. Now, the main question is how to choose the leaders. So, in the original, okay, so as I mentioned, after the ith iteration, the number of vertices survived is equal to the number of leaders in the current graph and the number of non-leader vertices which has no leader neighbor, because all the non-leader vertices which has at least one leader neighbor will be contracted. So we want to choose a small number of leaders, and at the same time, we want to make the number of non-leader vertices which has no leader neighbor small. And in this original paper, they choose each vertex as a leader with probability 1/2. In this case, in each iteration, you always have a constant fraction of the vertices as the leaders. And for each non-leader vertex, with constant probability, it will have at least one leader neighbor. So each time we can contract a constant fraction of the vertices. So we can do the connected problem in log n number runs. And actually, this is almost optimal for the path graph, because if you choose the leaders with probability which is larger than a constant, for example, which is larger than 1/2, then you will have many leader vertices. And if you choose probability which is smaller than the 1/2, then there will be too many non-leader vertices which has no leader neighbor. Question?
The graph is sparse. Will the second number in that equation, so will the non-leaders with no leader neighbor blow up and might ruin the algorithm? So what's your question? Because in the algorithm they need to choose a strategy to choose the leaders. So. Well, if the graph is sparse, then there might be a lot of non-leaders with no leader neighbor, right?
Right. So
does that blow up the run? Does that potentially mess up the runtime?
Right. So okay. So yeah, this is a good point. So our algorithm will make the graph be dense, and then when the graph is dense, then we can make a lot of progress. After we get a lot of progress, then the number of vertices survived will be smaller. Then we can make the graph denser. So when the graph is denser, then we can make more progress. So I will talk about it later. But this is a very good point. So for the sparse graph, it's very hard. But our point is we can make this graph dense.
Do you have to use probabilistic selection? I mean,
Yeah, right.
But what can you do it without?
Good question. So this is one open problem I will mention in the end of my talk. Okay. So, but if you choose each vertex as a leader with probability 1/2, then it always needs log n number of runs, because in each iteration you will always choose a constant fraction of the vertices as the leaders. So this is not what we want, because this needs log n number runs. So can we do better? If the graph has a better structure, as you mentioned, if the graph is dense, then can we do, what can we do? Okay, so we can look at a special class of the graphs. So it's called a high degree graph. It's a graph with n vertices, and each vertex has a degree at least d. Here, d is just a parameter. It's just a threshold. It can be any value, like a constant or log n or poly, but it's just a parameter, and you can choose this parameter. So for a high degree graph, which has the vertices each with degree at least d, if we choose each vertex as a leader with a probability log n over d, then with high probability, the good things will happen. The first one is that the number of leaders will be about n over d, because you choose each vertex as a leader with probability log n over d. And furthermore, each non-leader vertex will have at least one leader neighbor. This is because of the Chernoff bond, and you can union bond all the vertices. Then it means that after we do the contraction, all the non-leader vertices will be contracted, and only the leader vertices will be survived. But as I mentioned, because the number of leaders is just n over d, so only 1 over d fraction of the vertices will survive. Here's an example. So you have this 2 clique connected by 2 edges. So each vertex has a degree at least 5. So it's a high degree graph with the degree threshold 5. So we want to choose a 1/5 fraction of the vertices at the leaders. So we choose each vertex with probability 1/5. Then suppose we choose these 2 random leaders. And as you can see, each non-leader vertex has at least one leader neighbor. Then we can do the contraction. Then after we do the contraction, only a 1/5 fraction of the vertices will survive. So we make a huge progress. Now the problem remaining is how to convert a general graph to a high degree graph. So our goal is for input graph G, we want to output a graph G prime such that the graph G prime has uniformly large degree. So each vertex has degree at least d. Furthermore, the graph G prime has the same vertex set as the graph G. And G prime preserves the connected components of the graph G. So instead of find all the connected components of the original graph G, we want to find all the connected components of this high degree graph G prime. So one of our main contributions is to design a following MPC procedure. It calls neighbor increment. So for the neighbor increment procedure, we take n vertex graph G and the degree parameter d as the input, and it will output a graph G prime. And this graph G prime preserves the connected components of the input graph G, and each vertex in this graph G prime has degree at least d. And notice that if a vertex in a connected component whose size is smaller than d, then that connected component in graph G prime will be a clique. Okay. And this neighbor increment procedure takes log diameter number runs. The diameter is of this graph G. And this procedure needs total space, which is the number of machines times the local memory size is n times d squared. Notice that this procedure can work for any local memory size. We only care the total space. So if you have this total space n times d squared, you can always run this procedure. Okay, so before I talk about how to implement this procedure, let's say how to use this as the building block in our final algorithm. So here is our final algorithm. So for input graph G, firstly we just do the initialization, the iteration counter I, and let G1 to be input graph G. And as before, if each single vertex is a connected component, then we can just output the connected components. And then otherwise, we want to make the graph dense. So we want to construct a high degree graph. So we set this degree parameter in the ith round di to be the square root of m over ni. So m is the total space you have, and ni is the number of current vertices. So I will talk about how why we should choose the di to be this parameter later. And then we run this neighbor increment procedure. It takes the current graph gi and the parameter di as the input, and it will output the gi prime. So just remember, this graph gi prime will preserve the connected component of this input graph gi, and each vertex has degree at least di. Furthermore, this procedure takes log diameter number of rounds. But this diameter is the diameter of this graph gi. There's an observation that because the graph gi is obtained by contraction from the original graph g, so the diameter of this graph gi should be at most the diameter of the original graph g. So this log diameter, you can just use the diameter of the original graph g. And the total space you need is ni times di squared. Because di is chosen to be the square root of this quantity, so we know that the total space we need is just the order m. This is the total space available in the system, so you can run this procedure. After you run this procedure, you have a high degree graph. So you can choose each vertex as a leader with probability about 1 over di. And as I mentioned before, with high probability, each non-leader vertex will have at least one leader neighbor. So we can do the contraction. We can contract all the non-leader vertices. And as I mentioned before, if there are multiple choices, then you can just choose an arbitrary one. And then we let gi plus 1 to be the contracted graph. And then we can repeat the previous procedure until each single connected component contract to a single vertex. Then we can cover each vertices. Okay, so now let's analyze the number of iterations of our algorithm. So just remember, in the ith iteration, we set di to be this quantity, and the number of vertices survived after the ith iteration is about ni over di. So we can plug in the di in this formula, then we can get the following calculation. We know that the number of vertices survived after ith iteration is the number of original vertices over some quantity. And this quantity is double exponential in the number of iterations. This means that after log n number of rounds, log n number of iterations, our procedure will stop. And notice that in each iteration, we run a neighbor increment procedure, and it takes log diameter number of rounds. So the total number of rounds needed is just log d times log n. Okay, so now let's go back to the neighbor increment procedure. So how to implement the neighbor increment procedure? We propose the following truncated broadcasting scheme. So before I talk about this procedure, for the notation, we use the gamma v to denote the neighbor set of vertex v. Okay, so we just initialize this I, and then we initialize the neighbor set of v to be the original neighbors of v and v itself. And then in the ith round, if every vertex v has neighbor set size at least d, then we can just stop the procedure because it already satisfied the requirement. Otherwise, we check for each vertex v. If the vertex v has neighbor set which has size at least d, then we just do nothing for this vertex. Otherwise, if the vertex V has a neighbor set which has size smaller than D, in one case, there's a neighbor of vertex V which has the neighbor set has size at least D. In this case, we can make all the neighbors of U be the new neighbors of V. So after this round, the neighbor set of V will be at least D. In the third case is the worst case. So the vertex V has degree less than D, and all the neighbors of vertex V has neighbor set size smaller than D. In this case, we just do the broadcasting. We make all the neighbors of V be the new neighbors of V. Okay, so here is the procedure. Now, let's analyze this procedure. Firstly, we care about the total space. For the total space, if in the ith round, for the vertex V, if it already has degree at least D, then we just do nothing for this vertex. So there's only constant. So there's no extra space induced by this vertex V in the ith round. In the second case, if vertex V has degree less than D, but there's a neighbor U which has degree larger than D, then we just make all the neighbors of U be the new neighbors of V. So in this case, the extra space induced by vertex V is just at most D. Notice that if vertex U has the neighbor set which has size which is much larger than D, we can just keep the first D neighbors.
That's not what that line says, though. That's very important if you're going to control the space.
Right. Because for the space limits, so I just omit that. But I will. So it's very important. If you have neighbor set which is larger than D, you should truncate it. You just store the D neighbors. Okay. So in the third case, if in the ith round the vertex V is in the third case, in this case because the vertex V has at most D neighbors and each neighbor has at most D neighbors. So the extra space induced by this vertex V is at most D squared.
You have to ensure that the D squared number is less than the than each processor space, right? So each processor's space.
Oh, you don't need that. Yeah, actually. Okay, so I think Bob and Cliff, they have some improvements. So, for example, you can make D be much smaller than the local memory. So, for example, square root of the local memory size, and because the local memory size is m to some constant, after that you can make D be the constantly the same, be the square root of the local memory size, and then it will take a constant number of rounds to get your final results. But actually, for our algorithm, it's much more complicated. But you don't need to make the D be much smaller than the local memory size. You can use the sorting technique and use that B tree technique to do the to copy the neighbor sets distributedly and do the connection parallelly and in distributed way. So you don't need to make D be much smaller than the local memory size. It can be larger than the local memory size. You can still do that. Okay. Okay, now let's analyze the number of runs of this procedure. So in the first case, so in this case, if vertex V has neighbor sets which is already at least D, then in the remaining rounds, the vertex V will always has degree at least D. So it always satisfies the requirement. And in the second case, if vertex V has a degree smaller than D, but it has a neighbor which has a large degree, then in this case, after this round, vertex V will always have degree at least D. And in the third case is the most complicated case. So in this case, the vertex V has degree smaller than D, and all the neighbors of vertex V have degree smaller than D. So after we do this broadcasting procedure, after this round, the vertex V will still have degree less than D. However, we can show that in the ith iteration, in the ith round, if vertex V is in the third case, then the neighbor set of V will contain all the vertices which have original distance to V at most 2 to the I. Actually, we can prove this by induction. So at the beginning, because we just set this gamma 1 V to be the original neighbors of V union the vertex V, so it will satisfy the base case. And in the ith round, if the vertex V is in the third case, then we consider a vertex X which has distance to V at most 2 to the I. Then there should exist a vertex U which has distance to X 2 to the I minus 1, and the distance from U to the vertex V is also at most 2 to the I minus 1. So this vertex U should be in the neighbor set of V, and the vertex X should be in the neighbor set of U. So after we do this broadcasting, the vertex X will be in the neighbor set of V. So this means that this procedure will take at most a log diameter number of rounds. So while our main result is log diameter rounds connectivity algorithm, our techniques can be applied to related graph problems. So for example, for the spanning forest, we can still do it in log diameter times log n number of rounds. And the byproduct of our spanning forest algorithm is a diameter estimator. So we can output a d prime, which is at least the diameter of the original graph, and is at most the diameter to the log n. And we can find the DFS sequence for a forest by applying our spanning forest algorithm and our connectivity algorithm. We can also use this algorithm to solve the exact or approximate minimum spanning forest problem and the bottleneck spanning forest problem. So here's some open problems. So can we get a log diameter rounds algorithm? Because in our algorithm, we have additional log n factor. But I believe the true bound should be log diameter. So how to get this? And is it possible to design a simple deterministic algorithm? So because our algorithm uses the random leader contraction technique. So I don't know how to design a deterministic algorithm. So that's all, thanks.